Thanks for the introduction, Oleg. As he has introduced, the originally expected presenter should be Professor Li Jingguo, but unfortunately, he cannot come to USA due to his visa application delay. So I will make the presentation on behalf of Professor Guo. I hope my presentation will meet the standard of plenary talk, and I also hope I will not make you disappointed. Today I will talk about the solar hydrogen harvesting light and heat from sun. First, introduction. As we know, China is very rich in solar energy. Theoretically, it has 1,700 billion TCE every year, and two-thirds of the land surpassing two-thirds of the land surpassing 2,200 hours a year. It equals 5,000 megajoules per square meters. It is most abundant in western regions of China, as has been said by the previous presentation. The Tibet region is especially rich in solar energy. One of the efficient pathways to produce hydrogen by solar energy is to convert solar energy into hydrogen, because hydrogen as an energy carrier has the advantage of high energy density, clean, storable, transportable, and renewable. The source is only sun and water, and by production of hydrogen, and it can be used as a fuel for the fuel cells to produce electricity for civil utilization, and the final product is also water. So we can go to such circle with zero emission. The key is to making hydrogen a commercially viable clean fuel. Fortunately, the fuel cell vehicle has been sold commercially December 2014. It is fueled by hydrogen. It has cruising range of 700 kilometers and a max speed of 175 kilometers per hour. And it has a very large power and torques. And the most important is that the refueling time is only 3 minutes. That is promising. That make us more confidence in the hydrogen production. The outcomes of our group is the photocatalytic and thermochemical conversion solar energy to hydrogen. In this way, we can use both the UV visible part of solar energy and also the infrared part of solar energy. The first, light-driven hydrogen production. As we know, the artificial photosynthesis, with the input of or introduction of solar energy, we can splitting water into oxygen and hydrogen. And the hydrogen, in combination with carbon dioxide, can form the hydrocarbons. That is the fuels that we expect. The first example of photocatalytic effect is Fukushima-Honda effect. And lately, the particulate system is developed by BART. It also called BART system. Our work is to develop material that have the response for the UV, and besides the UV part, it can also respond to the visible light visible part of the solar light. And we also do some research on the material evaluation, such the reactor design, the instrument for material preparation and screening. The general requirement for the semiconductor photocatalyst is one to absorb as much sunlight as possible. That need way to develop semiconductor with visible and near infrared absorption. The second is to have energy band structure that is matching with the water splitting potential requirements. The most important is to enable effective separation of photo-generated electrons and holes. As it requires that the semiconductor should have long carrier lifetime. And also, we need the photocatalyst should be low cost. Then the earth abundant elements is preferred. And it should be easily fabricated. It also should be durable with long lifetime. What we will talk about is to enhance the charge separation. We have a review paper published in Chemical Review in 2010. It addresses the enhancement of charge separation. First, I will talk about the all oxide-based PEC water splitting. The most very important, the most famous is the silicon. Some important work has been done by Jacob from Caltech, and our work is focused on the tungsten oxide and bismuth, vanillate, and also alpha halide. The most important mission is search for low-cost, also for the low-cost, high-efficiency photoelectrode material. First, we have prepared some tungsten oxide nanowell and nanotube arrays, and by deep spinning, and we form the seed layer, and then by hydro treatment at 180 degrees Celsius for 2 hours. We have nanowells, nanoflakes first, and nanoflakes two. With different preparation conditions, we got different morphologies, different thickness, and different crystal structures. As we can see here, by the optical property, we got different optical response. And for the NF2, the nanoflakes 2, we have the smallest band gap of 2.51. I think most of you like the yellow color because this indicates more absorption of light. NF2 film also has the highest saturation photocatalytic value, and it has been attributed its narrow band gap. We also have determined the electron transport times by IMPS, and we found that NF2 also shows a longer transportation time, and we found that it have efficient electron transportation even in longer transfer distance. Secondly, we prepared bismuth vanillate nanowell arrays by aqueous chemical growth. With the different temperatures, we got different morphologies. At the higher temperature, we got the single crystal nanorods. At the lower temperature, we got nanoparticle stacked nanorods. And the most important is the steering for the formation of such nanorods. With this material, we have the quite high PEC activity. Finally, we try to make nanorod heterojunction by modification of bismuth finite on the tungsten oxide nanorods. Such heterojunction shows very high PEC activity, and also we can see the type 2 alignment. This is illustrate of the type 2 alignment for the charge separation. We also do some works in the alpha halide. This work has been introduced by Professor Shen, so I will not go into details about that. As we can see, by modification of titanium oxide nanodots, the halide nanorod will show high activity due to the quantum mechanical tuning process. Next, I will introduce cheap photocatalytic hydrogen production in our group. The aim is to find a simple and cheap material without loading. One example is we have successfully prepared microwave by microwave hydrotreatment, and we got combined oxide nanodots. The preparation time is very short, only need 30 seconds. And we can see from the image that the nanodots show the quantum size effect and the narrow light assumption. And most importantly, it shows the activity for pure water splitting. And we also found that it shows very stable activity for more than 240 hours for pure water splitting. The other work is the heterojunction. One is for example, cadmium sulfide enwrapped by titanium nanotubes. And this is one example of heterojunction. But it's possible to form junctions with single atom interface to reduce interface charge recombination. So what we have made is homojunction. This is a representation of zinc cadmium sulfide. The red atoms is it should have been in all atoms should be in one plane, crystal plane, but due to the twinning, it deformed. And this is image for the strip-like structures and the formation of twinning. And we found the materials or the solid solution with twinning structure shows high activity than that without twinning. And the ESR signals shows the longer lifetime of free electrons. It also indicates that the twins will be beneficial for the charge separation. This is illustration of the morphology of our one-dimensional nanotwin structure, and by the formation of zinc blind and water side alternative phase and the long-range ordered band alignment, we can control the aspect ratio of the nanorods by using various concentration of capping agents. This is a result for hydrogen production. As we can see, with the aspect ratio increase, that means if we have the long or thin nanorods with twinning, we have higher hydrogen production activity from 9% to 62%. By calculation, we found that in this structure, ZB phase have both higher conduction and valence band. So we can make such long-range ordered band 2 alignment for the charge separation. The other work of our work is development of pilot scale demonstration of hydrogen production. As we know, photocatalytic particles will disperse in water, and from the engineer point of view, there will many kinds of flow. For example, heterogeneous floating flow, moving bed flow, and fixed bed flow. By mathematical method, we can predict the phenomenon of solid-liquid two-phase flow in tubular reactor. We also use mental color method and light tracking method. We can simulate the light distribution on the surface of CPC. CPC is a reflector on the tube surface, and the light distribution inside the pipe. Also, with the use of CPC compound parabolic collector, we can predict the light distribution within the react tube. Also, we have tried to develop new solar concentrated reactor by combining different CPC. As we can see from this slide, different CPC are integrated into one single unit, and we can mechanically adjust the angle of the reflector to improvement the solar light absorption. This is the figure that for the large demonstration in the building of our lab. It has been successfully for the hydrogen production under direct solar light, and the hydrogen evolution rate is more than 675 liters per day cubic meters. And the economic analysis show that if the solar energy conversion efficiency amounts to 6%, it will be 6 RMB per cubic meters, around $1 per cubic meters. The second, I will give a brief introduction of thermal-driven hydrogen production. As we know, biomass is very rich in Earth. It also has many kinds, such as rice straw, leaves, and etc. In our lab, we concentrate on the supercritical water. As we can see from this the right figure, when it is a critical point at pressure of 22.1 megapascals and the temperature of 374, the water will possess both the property of gas or liquid water with high diffusion and solubility, and thus, due to the homogeneous and fast reaction environment, we can got the supercritical water gasification of biomass. This result shows that the SCWG supercritical water gasification can treat the biomass especially with more water content or more moisture content. It's very important because pyrolysis technology cannot treat such feedstocks. And by thermodynamic analysis, we found that 600 degrees Celsius is enough for the biomass gasification, and after that we can get stable hydrogen production with very small amount of methane. Most of them is hydrogen. And we also found by the ideal exergy efficiency calculation that with various solar concentration, such as C from 150 sounds to 30 sounds, the 6 degrees Celsius is also quite enough for the hydrogen production with solar concentration. Next, I will introduce some of the gasification reactors in our lab. Actually, we have developed the autoclave reactors as early as 1997, and it is the first SCWD reactor operated in continuous mode in China. We also found that more hydrogen will be produced if we use a mixture of coal and biomass. This is one equipment of fluidized biosystem. With this reactor, we can avoid the problem of coke plugging. That is the most important problem for traditional reactor operated on mode. This is the solar-driven concentration system. The left one is a multi-dish concentrating system. With this system, the reactor is fixed, and it is not convenient. And then we developed the new concentration system with the highly state of 3D sound tracking, and then the reactor will now fix and needn't to move. This is a demonstration in a large treatment amount. The design parameter is 1.65 per hour, and the maximum solar concentrating power is 163 kilowatts. The demonstration also has been run for 1 year. This is the overview of the moving solar reactor, and with this solar reflector, this reflector, after reflection of solar light, the second solar concentrator will concentrate all the light into the reactor located at the house with, as we can house with blue roof. The main components of the whole system also we have solar oven, feeding and cooling system. We have heat storage system. If the sun is not very good, the heat will be stored by molten salt. And we also have some piping and control system. And economic analysis shows that our system possessing capacity affects the hydrogen cost most. The hydrogen cost is 25.5 RMB per kilograms. If the processing capacity is 10 tons per hour. It is competitive compared to other solar hydrogen production technologies. The last figure is the perspective of solar hydrogen or also the hydrogen economy. That is published by the article is written by V. Series. It is also the professor in our lab. I also acknowledge the Ministry of Education of China, Ministry of Science and Technology of China, National Science Foundation of China, and the State Administration for Export Affairs. That's all for my presentation. Thank you.